Welcome to Introduction to Composites. Today is the 5th day of this ongoing week, and what we will discuss today is how to calculate computationally, how to figure out the longitudinal modulus of a unidirectional lamina which has fibers which are continuous in nature. So, our discussion will not be relevant if the fibers are broken and they are short in length. So, computation calculation of longitudinal modulus. So, we will call it EL, longitudinal modulus. Now, before we start computing this, we have to understand what is happening in the system. So, I will make a picture. So, let us say this is what the sample looks like. And the fibers so let us say that this is my L direction, this is my T direction, and the direction in the third direction is T prime. So, these are all the fibers, and when I look at it from this end, I can only see their endpoints. And what I am trying to figure out is that if I pull this composite in this direction and I apply a force FL, can I compute the value of Young's modulus EL for this composite? That is our goal, that EL, how do I calculate this? Now, what do I know about this problem? I know that what is the volume fraction of the fiber, without that I cannot figure it out. I also know the Young's modulus of matrix, and I also know the Young's modulus of fiber. So, these are the 3 parameters I know, and using these 3 parameters my goal is to figure out EL. Now, when I am looking at this problem, I make some assumptions and I assume, and this is an important assumption. So, I assume that fibers are perfectly bonded to the matrix material. This is the first thing we assume, that fibers are perfectly bonded to the matrix material. The moment I say that, what that means is that when I apply the force in x direction, this body has an original length L, it will extend by some distance delta L, right. It will extend by some distance delta L, and if the fibers are perfectly bonded to the matrix material, then the fibers, the matrix and the whole composite will expand by the same amount. If they are not bonded uniformly, if fiber is loose, then fiber will not expand, but the matrix will expand. But if they are perfectly bonded, then the extension, so the consequence of this is that strains in matrix, composite, and by strains I mean longitudinal strain, that is in the L direction, longitudinal strains in matrix, composite and fiber are same. This is very important to understand. The second thing I would like to say, so this is based on how I make the composite. So, if I make it nicely and everything is well bonded, then this is what it means. So, the second thing I would like to state, So, this is the first thing, first observation. The second observation is that F is the total force I apply, F is the total force. Now, some of this force is being taken by fibers and some of the force is being taken by the matrix, right. And what is the relation between the force being taken by fibers, matrix and total force? It is that F total is equal to, and actually I will not call it F, I will just make it Fp, so just to be consistent with my notes. So, P total, so P total is what? P composite, right. The total force which is being experienced by the composite is equal to Pf plus Pm, and this is equal to Pc. So, let us do some math. So, Pc is equal to Pf plus Pm. I am just rewriting this relation. Now, what is Pc? Pc is the total force which we are applying on the system. So, what is that? That is equal to area of the composite, cross sectional area, which is this entire area, right. This entire area of the cross section is AC. So, this is equal to AC times the stress in the composite. Similarly, Pf is equal to area of fiber times stress in the fiber, and Pm equals Am times stress in matrix. So, I can write AC sigma C is equal to AF sigma F plus Am sigma M. Okay. So, I divide this entire equation by AC and I get sigma C equals AF over AC times sigma F plus Am over AC times sigma M. Okay. So, what is, again it is important to understand what is cross AC? AC is this entire area ABCD. What is AF? AF is the sum total of all the cross sectional areas of all these fibers, and AM is the area of the matrix in the cross section ABCD. So, if that is the case, then AF over AC equals what? Volume fraction of the fiber. AM over AC will be volume fraction of matrix. So, I put these results in my equation back there. So, I get sigma C is equal to Vf sigma F plus Vm sigma M. Again I am not assuming, I am assuming that there is not a lot of air in the system. Okay. So, what was our goal? Our goal was to find the Young's modulus. Now, Young's modulus of composite EL is equal to what? Stress in the composite in the length direction divided by strain in the length direction. So, I divide this entire equation by epsilon. And what does this become? This becomes EL. Now, epsilon L is the stress is the strain in the composite, but we have said that the fibers and the matrix are bonded perfectly together. So, this is same as stress in the L direction in fiber, and this is also same as stress in the matrix in the L direction, right. So, I can replace this by epsilon LF and I can replace this by epsilon LM, and then what is sigma f over epsilon f? This thing is Young's modulus of the fiber in the length direction, and this is Young's modulus of the matrix in the length direction. So, EL equals EF VF plus EM VM. So, this is the relation between volume fractions and moduli of the fiber and matrix and the overall modulus of the composite in the L direction. So, let us call this equation 1. I can reformulate this equation in slightly different form. So, what I do is that I divide this by EM. So, I get EL by EM equals VF EF by EM plus, and Vm is what? 1 minus Vf, right, and I have divided the entire thing by Em. So, I do not, so this Em is gone, and this if I rearrange I can write it as EL over EM equals, I take Vf common, EF over EM minus 1 plus 1, yeah. So, this is equation 2. So, these are the two forms, and just wanted to give you some perspective of how strong is the influence of the fiber modulus on the overall modulus of the composite. So, we will do an example very quickly. So, we consider what do we consider? We consider glass fiber and we consider graphite fiber. And if you look at their modulus and their the modulus of matrix, typically EF for glass fiber is approximately equal to 20 and graphite is much more stiff. So, EF over EM is approximately equal to 100. So, we want to compute this parameter EL over EM. See, if there is no fiber, then the modulus will remain as same as EM. We want to see that if we add even a small amount of fiber, how much does the modulus of the composite change. So, compute EL over EM for VF equals 10% and VF equals 50% for both fibers. Okay. So, how do we do? We actually just use this equation 2 directly. We plug in EF over EM for glass as 20%, 0.2, and VF as 10% or 50%, and we can compute EL over EM. So, we will just make a table. So, for glass and we have graphite. For glass EF over EM is is how much? EF over EM is about 20, and for graphite EF over EM is about 100, and so this is there. Yeah, and the first case is VF is equal to 10% and VF is equal to 50%. So, let us write down these numbers. So, you can do the calculations, but I will just straight away write the numbers. So, here, so what are these values? These values are for EL over EM equals 2.9, EL over EM equals 10.5, EL over EM equals 10.9, EL over EM equals 50.5. Okay. So, that is there. So, couple of observations, I mean these are simple calculations, but couple of important observations. Even if I put a 10% glass fiber in the matrix material, just 10%, it is not that we have to put a lot of glass fiber, just a small amount which is 10%, it increases the modulus by almost 3 times, and glass is not that stiff compared to graphite. Okay. Glass is only 20 times stiff than matrix, graphite is 100 times stiff. So, even small amount of fibers can rapidly increase the stiffness of the system, and then if you increase the fiber content, then if you increase the fiber content almost, so so it almost linearly it increases the stiffness of the system. So, it goes from 2.9 to 10.5, and the same trend we see for graphite fibers. So, even if we put small amount of fibers, we will start seeing the benefits in terms of higher stiffness for the system. So, this is what I wanted to say. So, remember we had originally the discussion on specific stiffness. What this calculation shows is that even small amounts of fiber can rapidly increase the stiffness. See, stiffness went up by a factor of 2.9 for the matrix, and glass density is maybe 2.4, something like that. So, the density of the overall composite has not gone up by that much, but maybe it went up by 20%, 25%, we can calculate it using the formula for density, but the stiffness went up by 300%. So, a specific stiffness, which is the ratio of modulus and density, it really went up significantly high, and those payoffs or those benefits you see even to a much larger extent in case of graphite fibers, because graphite fibers are light, they are actually lighter than water and they are extremely stiff. So, you start seeing benefits very significantly for such fibers. Okay. So, this is what I wanted to discuss in context of longitudinal modulus. Next, what we will look at in next 5-10 minutes is how is the load shared between. So, remember we have this picture and we said that some load is shared by the fiber and some load is shared by the matrix. So, now we will figure out how much load is shared by fiber and how much load is shared by matrix in the system. So, our focus will be load sharing. Between fiber and matrix. So, we have to get a feel of this. So, remember, strain in for this system, because it is perfectly bonded, strain in the fiber is same as strain in matrix is same as strain in composite. What is the strain in fiber? Sigma f over EF. Strain in matrix sigma m over EM, and strain in composite is sigma c over or sigma L over EL. C means composite, you can also write it sigma L. Now, so this is based on the fact that fibers are perfectly bonded to the matrix, and when you pull them, the amount of extension of fiber experience is the same as the amount of extension the matrix experiences. So, from this you can write sigma f over sigma m equals EF over EM. So, how much load is being, the stress which is being handled by matrix and stress which is being handled by fiber is in the ratio of the Young's modulus, this there. So, if the ratio is 20, EF over EM is 20, then fiber takes 20 times more stress, not load, because load is also associated with area. So, if the fiber takes, but the stress in the fiber will be proportionally higher. Similarly, you can also say that sigma f over sigma c is equal to EF over EC. Okay. So, let us keep this as one equation. Now, we want to find what is the ratio of loads, because we are interested in loads, how much load is being shared, because ultimately we have to see how much, because what we apply is load. Suppose I apply 20,000 kilograms of newtons of load, I want to see how much is being taken by fiber and how much is being taken by matrix. So, PF is the load shared by fiber, PM is the load shared by matrix. So, what is PM? It is the stress in fiber times AF, and what is PM? It is the stress in matrix times AM. Okay. Now, we just computed that this thing is what is same as this thing. So, I can write it as EF AF over EM AM, and what I can do is I can multiply it and divide it by what? By AC and AC. AC is the area of the composite. So, what is AF over AC? This is VF. And what is ACOM, this thing? VM. So, what I get is EF VF by EM VM. Okay. So, this is equation 2. So, this equation 2, it gives us the ratio of how much load is being shared by fiber and how much load is being shared by matrix, and what it tells is that if you want the fiber to take a lot of load, of course, this EF over EM should be high, and also make sure that VF over EVM is also as high as physically possible. And then let us see what is PF over PC. So, PF over PC is what? It is equal to sigma F AF, and PC is what? Load borne by the composite, and that is what? sigma f AF, this is the load borne by composite plus load by matrix, load by matrix. Okay. Now, you divide the numerator and denominator by what? Sigma m. So, you get sigma f by sigma m AF by sigma f by sigma m AF plus AM. Okay. What is sigma f by sigma m? It is EF by EM, right. So, what you get is EF by EM times AF by EF by EM times AF plus AM, right. And then you divide the numerator and denominator by AF. So, you divide this, numerator and denominator by AF. So, what do you get? So, you get EF by EM by EF by EM plus AM by AF. Okay. And you can still, this ratio of areas is same as ratio of volume fractions. So, load shared by fiber in relative to that by composite is EF by EM by EF by EM plus VM by VF. And we know that Vm is what? 1 minus Vf, Vm equals 1 minus Vf, right, if there is no air. Then I can write it as EF by EM by EF by EM plus 1 by Vf minus 1. This is what I get. So, look at this. So, this is equal to load shared by fiber and load borne by composite. So, this is the third equation. So, what does it mean? Suppose there is no fiber in it. In that case, volume fraction is of fiber is 0. If volume fraction of fiber is 0, I mean if there is no fiber, fiber will not share any load. What does this relation say? If volume fraction is 0 of fiber, then 1 over Vf will become very large, infinity. So, denominator becomes infinity, so obviously Pf will be 0. So, that makes intuitive sense. If fiber is, so the other thing is that if fiber volume fraction is even, so okay, so here is the thing. So, suppose EF over EM is very large, EF over EM is very large, let us say it is 100. So, numerator is 100, denominator is 100 plus some number. Now, let us say Vf is 0.1, suppose Vf is 0.1, what does this become? This becomes 10 minus 1, 9. So, it becomes basically 100 over 109. That means that even for 10 volume fraction, because EF over EM is very large, 100 over 109 means what? It is almost 1. Okay. So, the graph looks like this. So, let us say here I am plotting volume fraction and here I am plotting Pf over Pc. So, let us say this is 100%, this is 50, this is 25, this is 75, okay, and here it is 0.8. So, what we are going to plot is for different values of. So, if EM over EF over EM is 1, then it looks something like this. So, this is about 0.8. So, this is EF over EM equals 1, which means if the fiber and matrix are almost are same, then there is no difference between their behavior, right. So, whether you increase the fiber or you decrease the fiber, so this is a straight line, because the numerator this thing is 1, this is 1 plus 1 over Vf minus 1. But as you increase the fiber content, so suppose you increase the fiber content to the modulus of fiber to 2, so it looks like this. So, it goes like this. So, as I so maybe this is EF over EM equals 100, this may be 50, this may be 20, this may be 10, this may be 2, this may be 1. So, what this picture shows is that if I increase the stiffness of my fiber relative to matrix, then I do not need a lot of fiber to bear most of the load, right. Because even at small volume fraction, so for when EF over EM is 100, I do not need a lot of fiber, because so even at small volume fraction, maybe 10-15 volume fraction, most of the load is taken by fiber. Matrix, the role of matrix is what? Just to bind everything together and keep everything in place. So, this is very important to understand. So, what naturally we would want is that we want to maximize Vf as much as possible, but for practical reasons it is very difficult to increase Vf over 80%, because once you start having more fiber than 80%, the matrix material finds it hard to flow between all the fibers and stick them together. So, there may be lot of areas in the system which may remain dry and the matrix may not be able to wet. In such a case, our original assumption that fibers and matrix and composite, they have same strains, that may not be true, and in that case the actual modulus of the material may be a little less than what is being predicted by the relation which we have developed. So, this is what I wanted to discuss for today, and tomorrow we will discuss a new topic which is related to the failure of unidirectional composites in the length direction. So, with that we conclude our discussion for today, and we will meet once again tomorrow with a new topic in hand. Thank you.